Alright, now we're going to take a look at deep recursion, which is something that you're going to have to do a lot of in this class, I'm afraid. That is, like I said last time, it's where you've got like a list that has other lists in it, so like A, B, 1, 2, 3 maybe even, and then like C. Okay, so in this list, there's like the top level, which is just A, B, C, and then this giant list here. And then if you want to go deeper, then you have to go inside this list here, and you'll get 1, 2, and then another list, and then you could go even deeper and go into this this other list here. And basically, deep recursion will go into an infinite number of layer of lists. Well, not really infinite, because then it would take forever, but you know what I mean. Alright then, let me show you. So what is not a list, pretty much, is an atom. So like 5 is an atom. Oh, well, okay, so what is not a list is not a list. So not list, 4. Right, so I think atom is sort of just like not list. Sorry, I had in my notes here, atom. Alright. So, but anyways, that is the name of something that is not a list or a pair. Alright, so, let's do a function called count atom. Count atoms. Alright. And what it does, count atoms. And we'll put a star. Now, when you put a star on the name of a function, well, that's like part of the name, by the way. That's not like an operator. It's not the multiplication operator, but that means that it is a deeply recursive function. Generally speaking, that's what it means. Obviously, multiplication isn't a deeply recursive function, but that is just a star. Alright, so let's say this would be like A, B, C. Count atoms would return 3, because it got all those. But then if you put in that other list, if you put in something like count atoms A, 1, 2, C, then it would return 1, 2, 3, 4. So what is the base case going to be here? Let's say count atoms of an empty list. That is always going to be 0. Ah, I've hit the touchpad. Alright, there, 0. Alright, so let's define this. Well, okay, so we've got to do a bit more than the base case. Okay, so count atoms of the empty list is 0. Now, if it finds something in the car of the list that is not a list, like this, like A, then it can add 1 to the count atoms of the cover of the list. And that's, I mean, we've done this before, where we count the length of the list that way. Okay, but let's say that the car of the list is a list in itself. Then how are we going to find out the length of this? Do we have a function anywhere that can find out the length of this list? Now, of course, we have the length function, but that only does a flat list. And what if there's another list within this list? Like that. Well, you need a function that can count all the atoms within a list that's deeply recursive. Of course, we've got one here. We're defining it right now. So we just call it self. Alright. So let's define it. We've got all the cases here. Define count atoms lambda ls. Alright, so the first case is if ls is null. And we'll return 0, because the null list has 0 atoms in it. Now what if if it's an atom, since there's no atom thing in Dr. Scheme, unfortunately, we'll just see if it's a list. If ls is a list, and what did we say? Not if ls is a list, if the car of ls is a list. If car of ls is a list, then we have to run count atoms on the car of ls. ls. Of course, so we run it on this. Let's get rid of that, it's a bit confusing looking. Okay, so we run it on this, but what about the rest of this other of the main list here? C, D and E, let's say. So we'll run it on that part, and then we've also got to run count atoms on the rest of the list too. And count atoms is basically just going to be adding. You know, I really wish we had that atom function. That would be a little easier to understand. Okay, so let's just say not list car of ls. That means it's an atom. So we'll add 1 to the count atoms of the CUD of ls. Okay, do you understand that? So the first one is like A. So we just add 1 to the count atoms of the rest of the list. And then we'll eventually add it to 0 once it gets to the end of the empty list here. Alright, now otherwise, otherwise, let's say we don't know, otherwise it's a list. Okay, so either it's not a list or it is a list, so else means there's a list there. So we're going to add the count atoms of the car of ls. And what will we add that to? We'll add it to the count atoms of the CUD of ls. That's pretty nice, isn't it? Nice how you can just call a function, have the function call itself to keep doing what it does. Alright, so let's try this. Count atoms A, B, C. That's it, pretty easy. You should be able to do that. 3. Alright. Now let's do it with you know, that one I keep giving you an example of. 1, 2. B, C. That should be 5. Yep, it's 5. So it goes inside of there and checks that. Now what should I do next? I'm going to trace it. So the Petite Chess Scheme program, so I can show you what it's actually doing. Trace count atoms star. Alright, now I'll just paste this in just to show you that it's actually like going into that sublist there. Alright, see, it gets to count atoms 1, 2, count atoms A, it gets that in releases oh yeah, okay, A, and then it goes in, gets 1, 2, and it runs count atoms on 1, 2 and there, gets done with that, and the answer to count atoms 1, 2 is 2, and then it keeps adding that to count atoms of the CUD of the list, which is B, C, and that's of course 2, so you end up getting 5. So that is that's deep recursion. That's about the simplest example of a deep recursion function that that I could give you. Let's see if there's some other one here. Alright, well that's it for this introduction to deep recursion.